Welcome to Data Science Now, a podcast by Closter, about the latest trends in data science with your host, Fabio Vasquez. On this episode, we'll talk about the importance of math for machine learning and the relationship of both fields with data science. Follow us on social media at Closter Team. This is Data Science.
Hello everyone and welcome to a new episode of Data Science Now. I'm thrilled to be here with you again this week, and this topic, it's going to be very interesting. Before that, remember to follow us on social media at Closter Team, and that this is being recorded and it's going to be published tomorrow on YouTube, on Spotify, on different podcast systems like iTunes and Google Podcasts. Finally, I will be creating the newsletter that's going to happen tomorrow. So make sure to follow me on LinkedIn here so you'll get a notification when I publish my article. And when you're inside of the newsletter, click subscribe if you want to get that directly to your feed. So again, the topic of today is the mathematics of machine learning. And this is a very broad topic, and I'm going to divide it in three big parts. The first one is, why do we need math for machine learning? The second part will be the parts you need to understand about math to be able to do machine learning. In the third place, it's going to be about where to study, where to begin, or how to understand all these topics. So I'm going to get started by the first point, is that why do we need math? Before that, I want to make 2 points. First, what machine learning is. I'm not going to give a very technical definition of machine learning here. You may find that on the newsletter. I'm going to publish tomorrow. But in a few words, machine learning, it's the way of designing algorithms to extract automatically valuable information from data. So this definition of machine learning, it's good because it will help us understand why do we need math in all of this world. The central issue of machine learning is how to transform your information, your data, in a very meaningful way. So you're going to be learning, you're going to try to automatically learn good ways of getting your data in a shape that will make you closer to what you're trying to understand or find there. So where's the point of learning math in all of this place? The first thing you have to understand about data science, and I'm going to make the distinction here between the math for machine learning and the math for data science. That may be part of a different episode. I'm going to be talking about here how to build machine learning models, and machine learning is a part of a workflow for data science. You may need more things if you want to do data science in the math world. I'm just going to focus right now on the machine learning part of it. So let's think of a problem. Say you have some information, you have data about a process. It can be everything you can imagine. You can get some data from that, like from marketing, from retail, from healthcare, from banking. And so when you get all of that information, the first thing you have to think is that, okay, so you have that in a database. That's great. But how can you start building things that can help you predict something with that data? The first thing we do in machine learning and in the world of machine learning is try to find a way of representing our information. And the most common way of doing that is through vectors, matrices, and tensors. I'm going to give a little more detail on what's that very soon. But again, remember that normally we have data in our database, and when we bring that into Python or R, something like that, or Julia maybe, then you have to store that information in a way that you can apply transformations to that. And the easiest way we've found so far is by vectors, matrices, and tensors. So then comes the process of cleaning your data, exploring your information, finding like important things there, correlations, plotting your information. All of this is important. And when you are happy with the way your data is, when the shape of your data is okay, then you start thinking about building models. A model is an abstraction of reality. That's very important because when you're modeling, you need a way of getting information through the complexity of the world. You need to get all of that, and because that's not possible to formulate in an equation, you need to maybe assume some things, or you need to think that this is not the most appropriate thing, but it can work. And that modeling process, normally you have two ways of doing that. One is a statistical model, and the other one is an optimization model. So this is going to be important to very soon. And so the last part, when you are happy with the model you want to apply to your information to predict a variable, then you use numerical methods with the objective of trying to find and optimize some equations to get and predict that thing you want. So in the description I just gave, if you know about this, you know that I just talked about three things: algebra, calculus, and statistics. So that's why we need math to do machine learning, because we need a way to represent our information, that's algebra. We need a way to transform our information, that is a combination between algebra and statistics. We need then a way of creating your models and optimize some equation that I'll talk about very soon, and that normally is done by calculus. So I'm going to be talking about those three things right now, and I'm going to go to the next part of the session, and it's what do you have to know about math to do machine learning. In a few words, is calculus, algebra, and statistics, but it's not everything. Okay, I mean, these are very wide fields that people spend all of their life understanding. People are spending years, 10 years, 20 years, 30 years trying to understand just algebra or just calculus or just statistics. So the idea here is that you understand what do you have to study or what do you have to learn to be able to conquer the world of machine learning. So I'm going to start with algebra. That's going to be important because that's the way we can represent our information. So the basic concept here is that you have to think about what's algebra. Why do we need algebra and what is an algebra? I'm going to define algebra as something that can build a series of objects that can represent concepts. And also, it has to contain a set of rules to manipulate those objects. Normally, all of those objects are vectors, or matrices, or tensors. In the whole world of algebra, and there are several types of algebra, I think the most important one is linear algebra, because linear algebra deals with vectors and the rules of manipulation. If you change the word vector here to something different, you may have a different type of algebra. So when you say vector, you start thinking on this like arrow pointing somewhere, and that's okay. That's the graphical representation of algebra. And that's something we call analytic geometry. That I'm going to go into details about that later. But right now we care about what can be stored in a vector. If you think about Python or you think about R, what are you storing in vectors and how are they called in those languages? They're called arrays, they're called lists, and all of these things is what you use to store information there. It can be numeric information, it can be strings, booleans, it can be complex numbers, or so on and so forth. So in the world of algebra, and specifically linear algebra, this is what you really need to understand to start on, to be able to go there and read papers, to be able to go there and when you're using an algorithm and you need to go to the documentation of the platform like scikit-learn or Spark or TensorFlow or PyTorch, something like that, when you go there and you read their papers and you go and read their GitHub, they're going to talk about vectors and tensors and the way they manipulate things. So if you define a vector and you define the rules for manipulating a vector, then you can define something called vector space. And that vector space, it's interesting because it may not be that obvious for you right now, but it will help you define something called a linear mapping. And when you have a linear mapping, you can start thinking about functions. So that's going to be important. Another thing that is also important for vectors is in the world of algebra is that you can start thinking about groups. And sometimes you don't see that many papers or books on groups for machine learning, but that can be important as well. So when you have more than one dimension for your data, when you want to store more than one dimension there, then you start thinking about matrices. And a matrix is something very similar to a vector, but it normally represents a system of linear equations. So that's going to be important as well. How to represent multiple types of information in a set of equations. And when you do that, you normally start defining a matrix. When you start defining a matrix, there's a lot of things you have to understand that are useful because it's very common that you will have a matrix in your information. Let's say you have a data in Pandas, the library I talked about last week. So last week I talked about Pandas as the library for data frames in Python, and you have something very similar for R. If you think about what's the inside of a data frame, it's just a matrix. There are rows and there are columns, and you can perform some operations there. So you really need to understand the connection between vectors and matrices, and also the concept of a linear set of equations. And there's a lot of interesting things there. I mean, I'm not going to go into detail. I'm just going to talk about what you need to understand. But the matrices, this is something very important, as well as vectors. They can be multiplied, they can be summed. You can find an inverse there. You can multiply by a scalar, you can multiply by another matrix, and all of these things that you may saw when you were studying at school or college, they were like, okay, I need to understand this because this is math and we have to do that. But if you really go deep into these places of papers and books and all of this, then you start seeing that they have a lot of great applications there. So there are interesting things to think about when you think about matrices. And one of the things you have to understand is that we are using sometimes a matrix to represent a system of linear equations. And in that, you normally want to find the value of a variable. Let's say x1, x2, and x3. And we have different methods of doing that. Sometimes you have exact methods, like I'm going to mention two here. One is called the Moore-Penrose pseudo-inverse, and the other one is called the Gauss elimination. So and also Gauss-Jordan. So those things you should, if you don't know them, you should know about what is a Gauss elimination. And those are exact methods. Sometimes you don't get to really solve a matrix by an exact method. And this is going to be very important because then you need to define something that is called an iterative method. You need to iterate and find a way of iterate and finding an approximate solution to your variables. I'm going to mention 3 processes here. One is called the Jacobi method. The other one is called the Gauss-Seidel method, and the third one is the Richardson method. So you can find this in every algebra book out there, and it's a simple concept, but very powerful. So there's much more things that you need to learn about algebra. I may come back to that in a little minute, but some things I will not talk about because I don't have time is the concept of a base, the concept of a range, the concept of linear independence, the concept of an affine space, and an affine mapping. All of these things, again, you'll find in books for machine learning, you'll find in books for algebra and calculus as well. So make sure to search for these topics. If you are not, if you're not very fast writing and you are trying to write what I'm saying, don't worry because tomorrow in the newsletter I'll be writing all of these things. Okay. So I mentioned something very brief about the graphical way of representing a vector, and I talked about that like arrow in space, that you have some direction and you have some way of defining something that we'll call later a distance, and that's the realm of analytic geometry. We have a very tight connection between linear algebra and analytic geometry. And you may be wondering, why do I need to know geometry to do machine learning? But this is very important because when you get started with the world of geometry and the world of analytic geometry, then you can define something called an inner product. And that inner product, again, I'm not going to talk about like the philosophical meaning of an inner product, can let you induce a norm. And the word norm, it may be weird. What does it mean? But it will help you measure a distance. So when you start about these vector spaces, when you start thinking about like vectors, and you can define the inner product, and then you can define a norm, then you can define what's a longitude, what's a distance here. And that's very interesting because in the world of machine learning, sometimes you need to find distance between points and your fit line. I'm going to give you a very quick example. You may have heard before of linear regression. Linear regression is an algorithm that you start building a line to fit some points, and you need to define a way of measuring how good or bad is your model. So what you do is that you start measuring the distance between the points and the fitted line. If you cannot define an inner product in a norm, you cannot define a distance. So this is why we need geometry to learn machine learning. I'm going to talk about 3 very basic norms that are very useful for the world of machine learning. The first one is called the L1 norm, that is related to the absolute value of a vector. The second one is called the Euclidean distance or the Euclidean norm, that you may have heard of this from the Pythagorean theorem. A squared plus B squared is C squared. So that can define a distance as well. And the other one is called the Manhattan norm or Manhattan distance. Again, I'm not going to go into details, but you can find that in every algebra book. One of the other things that may be important for you to check are the concept of an angle, the concept of an orthogonal projection, and rotation. And another very important thing is the concept of when you're building and you're plotting a line, you need to define a system of coordinates. And so you may have heard of X and Y, you may have heard of X, Y, and Z, but there are many more things to do to learn there, like the polar coordinates, or even more hyperbolic advanced coordinates. All of these things may be weird for you right now, but if you, again, go start and read all of these articles and papers and all of these things from machine learning, you'll find that these clever people find a way of understanding how important is this for the world of machine learning and data science. Some things I will not have time to talk about are what is a positive and symmetric matrix. That may be important. The Cauchy-Schwarz inequality, it's also very important. The concept of a metric, that's something that you will find a lot in physics as well. The concept of orthogonality, orthonormality, and something called the orthogonal projection. So all of these things are not gonna be I got a concept that I have such a thick accent that orthogonal sounded like octagonal. Yeah, it's orthogonal. I'm sorry. So, by the way, if you have any questions on whatever I'm talking about, please leave a comment right now. I'm live here at LinkedIn. You may not have the chance to ask me a question after this about this topic. So if you're there and you're interested, please write a message right now. Okay, so far we've talked about two important things. One was the concept of algebra, linear algebra, all of these things, and now the world of geometry and analytical geometry. I'm gonna do a little. So there's something that we have to go back to algebra for a little while, because I need to define something very interesting. That is called the matrix decomposition. Matrices can be decomposed. And you may wonder, like, why is that important and why do I need that? And so you'll find a lot of different applications. Like if you think about how to build a recommender system, then you're going to need this. You're going to need to understand how to transform a matrix and how to decompose it. And when you think about this, you need to define something that will be very important for your life. If you don't know it right now, it's called the determinant of a matrix. You need to think about the eigenvalues, the eigenvector. You need to understand if a matrix can be inverted or not. What is an orthogonal matrix? How to create a matrix of only a diagonal of ones. How can you build that? So there are a lot of things here that I will not have time to talk about when you come about matrix decomposition. They are very important for the world of machine learning. One thing I can talk about that you have to check on online or in a book is called the Cholesky decomposition. Find that and read about that. You need to find also about something called the eigen decomposition. That's going to be important. Something called the singular value decomposition. It's going to be important as well. And the final concept of a matrix approximation. Great. So I think we've covered a lot of different things that you have to learn about algebra and geometry. And now, I mean, why is this important? Because this is the way you represent your information, and you need to start thinking on how you can manipulate this information. And algebra and geometry will help you do that. There are two more things that you have to learn very well. And we're going to go to the next one right now. And it's the concept of calculus. And calculus is just, again, a very big field that people are spending their whole lives learning. But let me give you a little history on calculus. Back in the 1700s, people were starting to think about how things moved. And one of those people was Isaac Newton. And when Newton was starting to think like, okay, so what's the concept of something changing in time, or what's the concept of something moving from here to here, and how can I find a theoretical method to define all of this? Then, because he was very intelligent, he didn't just say, oh, well, we don't have the tools for this. He just created calculus. And that's a very interesting thing to do. And at the same time, there was another person called Leibniz that developed almost the same theory. So you can find a lot of information and videos on like the history of calculus. It's very interesting and is closely related to the way things moved. So mechanics depend a lot on calculus, astronomy, and the whole physics. I think most physics is based on the concept that we have calculus. So what's important for you to know about calculus? You need to understand what is a function. And I briefly talk about functions when I talk about the vector spaces and the matrices, but a function is something that can determine a quantity. It's like a quantity or an object that can relate two quantities. Okay, and sometimes we call that the domain and the image, or the domain and the range. And let me give you a very basic definition of a function. Let's say you have y equals x squared. So x, it's going to be your domain. All of the numbers that can be squared are in the domain of x. And the function is this object that is squaring the x. It's a linear mapping. And not every function is linear mapping. You can find like more complicated things to do, but in general, a function is a linear mapping. It's mapping the domain and the range, or the domain and the image. And basically, you have this thing that is transforming your x into an x squared, and then you're storing that into y. So y is going to be the image or the domain. You may have seen this before, but they're like two circles. And you have one line that is like putting things from the circle 1 to the circle 2, and this is a function normally. When you define a function, you can start thinking about much more things. And one of the interesting things, this is again very big, and I'm going to do a massive leap here, and I'm going to go to the world of differentiation. When you start thinking about a function, you can start thinking how this function can change on time, on space, or whatever you want. So when you start thinking about differentiation, normally what you do is that you're applying geometry. And this is something very particular. If you really want to understand calculus, I really recommend that you also understand geometry, because a lot of the concepts of differentiation and derivatives, we're going to go very soon, are closely related to the world of geometry. And if for some reason you manage to get your hands in the Newton's Principia, this Principia were the books where Newton was talking about like the laws of mechanics. In here, he found a way of actually building and demonstrating and prove his theorems through geometry. It's a very complicated book. Maybe don't read the demonstrations, but read the concepts. It's a very good and interesting book. So let's go back to differentiation. Differentiation will help you build something that can be related to the way a function is changing in space or time. And normally, the way of doing that is calculating the slope of a line that is called a secant, and this line is 2 points in a graph. So if you calculate that line there, the slope, then you can start thinking about something called the differentiation of a function. When you apply limits, and this is something you need to understand very basically at least, what's a limit and what does it mean for the world of calculus. When you apply a limit, when in the definition of the differentiation, in the bottom of the equation, you have a differentiation over a variable. Let's call that variable x. when you go there and you start thinking about when you go to the limit, like to the a very infinitesimal like distance for the points of the second, then that second will be transforming into a tangent. In that point, the line that you're calculating the slope, it's going to be only touching the other graph or the other function in one point, and that's called a derivative. So why are we talking about derivatives? Why are they important? Remember to always keep thinking about why we learning things. If not, you're going to get lost in definitions and complex notation, and you're going to get frustrated. We're learning math because we need a way of optimizing functions. We need a way of finding a way of propagating errors between our iterations. And this is why and machine learning is basically that. So we will need calculus to be able to define a derivative and something called a partial derivative. A partial derivative is very similar to a derivative, but in this case, you have that one function can depend on more than one variable. And when you apply the derivative of a function that can depend on more than one variable with respect to one variable or more, but not every one of them, then you're creating a partial derivative. And again, you may be wondering, why do we need to have a definition for a partial derivative? Because that can help you define something called a gradient. And when you start thinking about a gradient, then you can start thinking about the way things can be optimized or changed, or like how can you move through the space of a function to find its minimum, its maximum, or something like that. So when you define a gradient, then when you do that, you can start defining ways of optimizing things. This is very related to the concept of finding a minimum in a function, finding a maximum in a function. And this may sound weird, but all of this is what we do all the time in machine learning. What we do is that we go there and we find the gradients, and one of the most important algorithms of the last 100 years maybe was the gradient descent. You may have heard of this before. And gradient descent is a way we have to finding a local and global minimum or maximum for our functions, and this is the way we can optimize and find something. So you may start thinking about, like, why do we need to minimize or optimize something? Like, why do we need that? Let me paint you a little story here. So let's say you're trying to predict for how much you should be selling your house, okay? And you think about that the only important variable for you is how big is your house. So then you start thinking about, I want to build a model that, depending on the size of my house, I can know, or I can find for how much should I sell it. So you start gathering information from the web, you start finding information in other places, and you build your data set. That you have the size in meters or something like that, or meter square, and you have something here that is the price. So you have for 1 meter square, you have this price. For 1,000 meters square, you have this other price. And then you start plotting the data you have. Let's say you plot X and Y. You plot the size of your house, and you plot for how much you're selling it. And it's very probable that you will find a line that is going like this. Okay, it's going to be an upper right growing line of points. Okay, for each point of money, or like dollars or whatever you're using, and 1 point for the size, and you start building points, and then you think, hey, I can apply here linear regression. Then you start thinking about, okay, great, and This is very cool. And in here, I talk about the concept of distance and all of these different things. And so you build a model there that you can use different ways. One of the most common ways of optimizing this process is something called the sums of minimum squares. And in there, you're not doing derivatives a lot, or you're not doing all of that. But if you go into details of how this is programmed in Python or R, and you start thinking about more complex algorithms like logistic regression, something like that, then you find that if you want to find like the best set of parameters for your model, and this is important, machine learning is finding the best parameters for your equations. So what you do is that you say, there is an equation that will help me find for the best price for how many meters squares my house is, how much shall I sell it? Okay, or it's gonna find with these three variables if I should be giving this person a credit or not. So for finding those parameters, you need to optimize. And that the process of optimization there is normally done by something called gradient descent. And that is a process of applying derivatives to something that we normally call a function, an objective function there. And this function here, or loss function, is also called. When we derive and we apply a derivative to our loss function, then you can start thinking about optimization, and then you find the best parameters that give you the least errors. So the word error here will be very important because it will start a new topic that's going to be statistics. So again, we talk about algebra, geometry, and calculus. All of this is important to be able to store your data in something that you can transforming your data, to graph your information, be able to create plots from that, and to be able to understand graphically what's happening, and to optimize the process. In the beginning of the session, I talked about that normally when you build a model, you have two ways of doing that. You have an approach that is an optimization that is closely related to the world of calculus, and the other one was a probabilistic definition. So I want to go to statistics and probability, and I'm not going to have the whole time to talk about it, but it's one of the most important things you have to understand if you really want to master machine learning and data science. Statistics and probability is the study of data. So the evolution of statistics, I'm quoting here several people in the 2000s, like Leo Breinman and Jeff Wu. They said that the evolution of statistics was the data science. So we come from statistics. It's like the father of data science. And why is that? Because in there you can start thinking about how to define a variable that can start define something called a probability. And a lot of the things we have to do are not exact methods. I briefly talk about the concept of a method that can be iterative with your information and stuff like that. So statistics is a way of finding a lot of different things like errors, distributions, transformations, and all of these things you need to master. If you need to master something to be able to understand the math from machine learning, is statistics and probability. When you have all of this, you can start thinking about the rule of the products. You can start thinking about the Bayes theorem. You can start thinking about distributions and what's your information saying to you. Do I have a normal distribution? Do I have a different type of distribution? You can start thinking about ways of finding things from your data, like the mean of your information, the statistical, the standard deviation for your information. How is my information different from this? And all of these different things. So the concept the concept of statistics and probability are huge in the world of data science and machine learning. You really need to master those. And you need if you really want to master statistics, you really need to understand the normal distribution. The normal or Gaussian distribution is the most important distribution we know, and we really understand that. If you ask a physicist what they know, they should be telling you that they really understand the harmonic oscillator. If you're a physicist, you know what I'm talking about. If you are a data scientist and you say you know statistics, you really need to know the normal distribution. Because a lot of the things we can do for machine learning depends on our data being normal, being standard. So we have a lot of different things that it's statistical tests. We need to find a confidence interval for our results. How are we going to measure how wrong or good are we in our final results? If you say to your manager, and your manager knows statistics, and you're a data scientist in a company, and he's asking you to predict the next period sales, and you give him or her only the number, like we're gonna sell $2.5 million next month. If you just give that, he knows that you don't understand statistics and data science. You need to give errors. Nothing that we do in data science, I think 99% of what we do is not exact. It's not exact. So we need to find a way of defining errors. And the other, the last thing is that if you go to deep learning, something that we've not covered here, and deep learning is a part of machine learning, then you have something called the backpropagation process for errors, and that's even more advanced in the world of calculus and stuff like that. But in there, you also need statistics. If you want to know deep learning and all of these great computer vision, NLP algorithms, the things Google is doing, the thing Amazon, Facebook, LinkedIn's doing, you need to understand statistics, you need to understand math, you need to understand calculus. So to end this session, I'm going to talk about very briefly on where to learn all of these things. I had a call today with a student, and he was asking me the same, where can I learn all of these things? Because this is hard, and this is not an easy piece. So I'm going to give you 3 ways of learning this. The first one is you get formal education. You enroll in a school. You take 4 or 5 years of calculus, an engineering or a science. You graduate from physics, from engineering. You are a biologist. You start learning applied math. And that's the formal way of doing that. There are a lot of great schools in the whole world. In your country, there's probably something very good teaching that. If not, you have a lot of online education. I mean, formal online education, not courses, but you can take a whole career online, or you can do a master's online on all of this. The second way of doing or learning all of this is from researching, reading papers, and taking online courses. Right now, I work for a company called Emeritus, and we have a lot of different courses there. If you want to know more about that, you can reach to me through LinkedIn, and I'll tell you more about that. And as I mentioned in other episodes, I'll be launching courses on data science as well. They're going to be in Spanish for the first part of this year. So I'm going to be launching courses for Python and data science and statistics. So if you speak Spanish, make sure to follow Closter on social media and also on LinkedIn, because you'll find information there. And the third way of learning all of this is through a mentor. And a mentor and doing projects. Okay, so what does that mean? You can enroll into a system of like Kaggle, or you can find a challenge online to solving this problem. Sometimes they need people that are not expert, they just want to learn. And you're not going to get paid for this, probably, but you can get a lot of great information out of this. And if you have that mentor helping you in that process of the project, then you can start thinking about, hey, so I want to perform here a linear regression. So that sounds very easy, and that's super simple to do in Python. That's 2 lines of code for real. But it's very dangerous that you think that machine learning and data science is being able to understand some libraries in Python or R or whatever. If you really want to master all of this, you need to understand your math. So I'm going to be publishing all of this in the newsletter with more information. My sister Hazel created some infographics for a talk I gave some months ago about this specific topic. So I'm going to be I'm going to publish the newsletter with all of these infographics as well. They're in Spanish right now, but I think I'm going to change them to English so all of you can understand that. And of course, I'm always happy to help you learn more. I'm always here at LinkedIn. You can talk to me, you can write me, and you can take my courses. So again, thank you very much to everyone here for being here. I have a comment here that's very cool from Edison saying, in other words, you need to understand math to learn and apply machine learning, and that's correct. You need to understand your math to be able to really apply and understand machine learning. So again, thank you very much to everyone for being here. Thanks to my great team, Gabriel, Eileen, and Hazel for helping me building this space for me to talk to you. And I'm gonna I'm gonna see you next week probably if everything goes well. Again here at LinkedIn Live, and remember to check YouTube and Spotify tomorrow if you want to get like a video recording or an audio recording of this session. Thank you very much. Good night. Have fun and be kind. Bye-bye.